Okay, so if there are no questions, then it's 11 o'clock. Let's continue from where we left off the last time. So on Monday, we started looking at chapter 4, right? And for chapter 4, that will be like the main section we're looking at for the exam, right? So the third exam will be from 4.1 to 4.9, right? So for 4.1, we looked at maximum values. So let me share my screen. Yeah, please, I'm sharing my screen now. If you can't see, do let me know. So we started looking at maximum values, right? And then we described what absolute maximum values were. And we also talked about where they occur, right? As I said, there are two things. We have the value and where it occurs. So you have to be careful what the question is asking about, right? Some questions can ask where it occurs. Others too can ask what the value actually is. So we did all that, and we said that to find the absolute maximum or minimum value, we're going to start by looking at local extreme values. And we concluded that for local extreme values, they are likely to occur, or they will be part of a set of points where the f prime at that point is equal to 0, or where the f prime is DNE, right? So we saw an example here, right? From Fermat's theory, we realized that the local extreme values could occur at the 2 points, right? For example, for this point, right, you see that the f prime of 0 is DNE, right? It does not exist, or the function is not differentiable as 0. We saw this way back in chapter 2, right? We proved that the function is not differentiable here, but you can clearly see that there is a local extreme value here. There is a local minimum value here, right, at 0. Right? So that means that when we are trying to find where the local maximum or minimum occurs, we have to consider 1, where the f prime is 0, and 2, where the f prime is does not exist, or the function is not differentiable, because it could occur at those 2 points. So with that in mind, we define something we call a critical number. So this is a very important thing you have to know going forward, right? You'll be using this term a lot. So what is a critical number, right? So this is a very important definition. Now, a critical number of a function f is a number c in the domain of f. So there are key points here that I want to draw attention to. So the first thing is the critical number is always part of the domain of f, right? It's a number c in the domain of f. So if the number is not in the domain of f, then it cannot be a critical point, right? So that's very important. So first and foremost, it has to be in the domain of f. And then either the f prime of the c is given as 0, or the f prime of the c does not exist. So those are the 2 points you have to look at, right? Either the f prime of c equal to 0, or the f prime of c does not exist. Now, what we are saying is if a function has a local maximum or minimum at c, then the c has to be a critical point. So among the list of critical points, you get points where there is a local maximum or minimum occurring there. But we're not saying that all critical points give you local maximum or minimum value. What we are saying is they will be in there somewhere, right? So the critical point includes everything. Please, I hope you're okay with this. Okay, so now with that said, let's try and look at an example of how you're going to compute a critical point. So let me make this big, and let's look at example 7. We have space here. The solution is not here, so let's work it out. So the question goes, find critical numbers of the function. So to find critical numbers, we first have to acknowledge the domain of the function, right? So we say, okay, for f of x equal to x to the 1/3 and then s minus 2, the question is, what is the domain? What the domain is, can anyone please help me with this? Do you know what the domain will be? What will be the domain for this function? Anybody? This will be very important. That's the first thing you have to find. Yes, what's the domain? Perfect. It's all real numbers. That's true, Leno. Thank you. So it's all real numbers. You can plug in any x and it won't be undefined, right? It's all real numbers. So for this one, the domain is all real numbers, which I'll denote by this. Right? So negative infinity to infinity is all real numbers. Now, after getting this, I know I have to check for 2 conditions. I have to check for where any c that will make the f prime 0, or where the f prime of 0 does not exist. Okay, so now let's see. So I just need to find f prime. So I get f prime of x. So f prime of x will just be d over dx. Because for either of the condition, whether f prime of c equal to 0 or the f prime is d, I need f prime. So the next step will be get the first derivative, right? So that would be d over dx of what? X to the 1/3 and then s minus 2. and then you try and differentiate this, right? So this one, we employ the product rule here. So because it's a product of function, so I'll say leave this one, multiply by the derivative of what? S minus 2 plus leave S minus 2, multiply by the derivative of what? X to the 1/3, right? And then I move on. Now for this part, chapter 4, this is where we will simplify a bit. Here we will simplify, right? Because if you don't simplify, you can't get to your answer, right? So this is what I was talking about. You see, in chapter 3, I said simplification is not the goal, but in chapter 4, we'll be doing a lot of simplification. So here, let's see. So for the first part, we have the derivative of S minus 2, which is the difference rule, right? So when you differentiate that, that's just going to give you 1. So you have X to the 1/3, right? And then plus X minus 2. And then this one, when you differentiate by the power rule, it will be 1/3, and then S to the what? 1/3 minus 1, which is negative 2/3, right? So you have something like F prime of X equal to X to the 1/3, and then plus, let me leave some room here, and then plus X minus 2, and then this is going to be over 3, and then S to the what? 2/3. This is going to be. But then you have to write this as a single quotient. You have to write it as a single quotient, right? So to do that, I need to check the LCD. The LCD is the least common denominator is 3s to the 2/3, right? So I'll multiply both the numerator and the denominator of this part by 3s 2/3, right? So that I can get a common denominator. I'm trying to write it as a single quotient, right? So moving on, I have F prime of X equal to, now for this side, S to the 1/3 times S to the 2/3. Since the bases are the same, I can add the exponent. So that's going to be X to the 3/3, which is S to the 1. So you get 3x for that one. And then I've combined these, so I have S minus 2 here, right? And then all over what? 3x 2/3. Please, are you okay up to this point? Any questions? Okay. Now, we can still simplify. Okay, I see something in the chat. Give me a sec. Can I finish? Yeah, sure. I'm not going to move on to the next slide yet. Isn't it 4x? Wait, did I make a mistake? Isn't it 4x since x times s? Oh, okay. So I see what you mean. You mean the combination of the x to the 1/3, this one, and then that one. So what I'm saying is, right, let me see. Yeah. So what I'm saying is, let me do that on the side here. Let me do that on the side. So that I'll continue on the next page. So what I'm saying is s to the 1/3. So note, right? S to the 1/3 times 3s to the 2/3, right? By the law of exponents, the x's are the ones with the same basis. So you do x to the 1/3 plus 2/3, and then the 3 will just be here. You see, the 3 doesn't have any other common base. So the 3 is pulled out. And then you do 1/3 plus this, which is 3x to the 3/3. And that's 3/3 is 1, so that's 3x. Let me see. I think I see another thing in the chat. Nice. You're welcome. Okay, so we are good then. Let me wait a little, right? So if you need time. Right. Also, if you don't understand any part, let me know. Okay, anybody still needs time here? Yeah, okay. Let me wait. Let me see. Okay, you're done. Okay, cool. So we are here, right? So let's try and simplify the f prime. I'm going to move on to the next. So we get f prime of x equal to, and then we have 3x plus x, which is 4x. Oh. So 4x, and then minus 2, and then all over what? 3x to the 2/3. Right. So this is where we are. Okay. So now that we have this, we try and find the critical point. So for critical points, you need to check for two things. After you get a derivative, you have to check for two things. You have to check for where f prime of x is D and E, and where f prime of x is equal to 0. You see, because those are the two conditions. And don't forget that any critical point we find has to be part of the original domain of the function f. So we consider the original domain. Okay, the original domain is all real numbers. Now, the first thing we are checking is where f prime is d any. What does it mean? Well, f prime of x being d any, it just means any x which was part of the original domain, which is now making f prime undefined, right? So when you look at f prime here, you can see that f prime of x is undefined when the x is 0. When the x is 0. And the question is 0 part of the original domain? Yes, the original domain is all real numbers. So that means we have a critical point here. So when s is equal to 0, right? So this is a critical point. We found it using this condition. Please, I hope you're okay. Right, so we have one value here. So for that one, you just consider the function f prime of x and check whatever makes it undefined. But please don't be quick to write the answer there, right? If 0 was not part of the original domain of f, then even if it makes the f prime undefined, it can't be a critical point. So please be cautious on that, right? It's easy to make such a mistake there. So it has to be part of the domain of f, and then it makes f prime undefined. That's the first condition. Now for the second condition, we have 4x minus 2 over 3x2 over 3 equal to 0. And then for this one, for a quotient to be 0, right, the numerator has to be 0. So that means you have 4x minus 2 equal to 0. And then solving this, you have 4x equal to what? 2, which will give you, divide both by 4, and you get s equal to 1 over 2. Right, so that means that you end up with critical points. So you assemble all of them. Critical points are, you have 0 and half. So these are critical points. Please, are you okay with this? Any questions? So that's how you find critical points. So first, get the first derivative, right? Get the f prime. Simplify it, right? If it's split up, write it as a single quotient. And then usually I'll advise that you don't simplify the numerator too much if it's like a quadratic or something, because you end up factoring, but it's all up to you. You end up factoring after setting the f prime equal to 0, but it's up to you. You can multiply it out and then you come and factor it again here, right? But if I have it factored in the numerator, I won't simplify. Now, after doing that, after getting the f prime, right, either writing as a single quotient or a single like expression, then the question is, I need to check for critical points. Get the f prime, right? You have the f prime. So check where the f prime is d any. And the question that you ask at that step is there any x which makes the f prime undefined, which was originally part of the f? If yes, then you list all those points. And then you go to the second condition, right? The second condition is f prime of x equal to 0. Is there any x which makes the f prime equal to 0? That means for that one, set f prime equal to 0 and solve for x. And then when you're done, all those points which satisfy the two conditions will be critical points. Yeah, please, any questions here? Anybody needs time? Okay, then let's move on. Now, the main goal of finding these critical points was to help us identify like local extreme values. But why were we finding local extreme values in the first place? Well, this whole process started from the extreme value theorem. And for the extreme value theorem, we are looking for what? An absolute maximum or absolute minimum. So now that we have knowledge on how to identify critical points, we define something we call the closed interval method. And this is the method which is now going to be used to find the absolute maximum and absolute minimum. So to combine knowledge from the critical point, we use the critical points together with some other conditions to figure this out. So the thing is, for closed interval method, it says to finally find the absolute maximum or minimum values of a continuous function, right? Because we learned from the previous session that if a function is continuous on a closed interval, by the extreme value theorem, it has to have an absolute maximum or absolute minimum. But now that we have the critical point, we know how to compute the critical points, we are now going to find how to work it out, right? How to get those extreme values when the function is continuous on a closed interval. So the thing is, if the function, to find the absolute maximum and minimum values of a continuous function on a closed interval a to b, then the first thing is to find the values of f at the critical points. So you first have to find the critical points, right? And then you evaluate the function at the critical points. And then we also saw from the examples that the absolute maximum or minimum could occur at the endpoints. It could occur at the endpoints. And critical points are usually in between, like the interval. So after finding, or it could also be at the endpoints, it doesn't matter. Now, after finding the value of the function at the critical points and then at the endpoints, you compare all the values. The biggest amongst them is your absolute maximum value, and then the smallest among them is your absolute minimum. And that is the closed interval method. Right? So first, find the critical points. Evaluate the function at the critical points and at the endpoints. The biggest amongst them is your absolute maximum value. The smallest amongst them is your absolute minimum value. And the x's that you plug in to get those absolute maximum or minimum are where the extreme values occur. Right? So you see an example very soon. But please, I need to move on to the next slide. Let me know if you need more time here. Okay, so that's a closed interval. Okay, so if you don't need time, let's move on to the example. Now, on your quiz tomorrow, you'll be identifying absolute, like where they occur, like local maximum, local minimum, absolute maximum. It will be a graph, like you identify where it occurs at. Please, it's where it occurs at, right? So read the question carefully. And then you'll be using the closed interval method. So you have a question like this, like a polynomial with on a closed interval, and you have to find the absolute maximum or minimum. It will mirror this question. So now, for this one, how do we know that we're going to use the closed interval method? Well, what I can see here is the function is continuous, right? A polynomial is continuous everywhere. So, okay, the function is continuous. It checks that first list of the extreme value theorem condition. And then the next thing is the function is defined in the closed interval. Okay, so the second list is checked, right? Second thing is checked on the list. So we know that, okay, this one by the extreme value theorem, there has to be an absolute maximum and an absolute minimum, right? So how do we proceed to find it? Well, the first thing is we need critical points. So how do you get critical points? Well, you need a first derivative. So finding the first derivative, this is a polynomial. So we do d over dx of what? Of 4s squared minus 16x plus 6. And then this derivative is just 8x minus 16. Nice, we have the derivative. Now this time it's a polynomial, so not a lot of algebra to do, right? So after getting this, the first derivative, for critical points, you need to check for two things. You need to check for, the domain here is from 1 to 4, right? So you need to check for where this is dne and where this is equal to 0. Right, so we start, okay, is there any x which was part of the domain of f, which is now making the f prime undefined? Well, the f prime is also a linear function, and the f prime is defined for any x. So there's no critical points for this condition. Right, so we check the second condition. So for that one, we have to set f prime of x equal to 0 and solve. So for this one, you get 8x equal to 16. Divide by 8, divide by 8, which means x equal to 2, right? So the only critical point we found is 2. Right, so that's the only one. Now, after getting this critical point, what you have to do is you're going to evaluate the function at the critical point and at the end points. Now, the end points of this interval are 1 and 4. Right, so just evaluate the function there. The biggest among them is your absolute maximum. The smallest among them is your absolute minimum. Yeah, please, I'll need to move on to the next slide. So do let me know if you need more time here. Okay, so we go, okay, so now let's try and get the absolute maximum and absolute minimum. So we do f of the critical point. So if there are many here, you do the function of each of them, right? So do one by one, right? F of 2. This one is also only just one critical point, so f of 2. And then you also have to do it at the end points. The end points are at 1 and 4. So you have to find f of 1 and f of what? F of 4, right? F of 4. So we are going to use the original function. What is f of 2? The f of x is 4s squared minus 16x plus 6. So 4x squared minus 16x plus 6, right? Yeah, so we just do this computation. So 4s squared, this is 16, and then 16 minus 16 times 2 plus 6. And let me do a little quick manipulation here. I can factor out 16. I have 1 minus 2 plus 6, and that's going to give me negative 16 plus 6, which is negative 10. Right, so this is one value. And then for this one, I do 4 times 1 squared minus 16 times 1, and then plus 16. Sorry, plus 6. And then that's just going to be 4 minus 16, and then plus 6. Now, 4 plus 6 is 10, and 10 minus 16 is negative 6. So I have this also. And then the next one is I have 4, and then 4 squared minus 16 times 4 plus 6. Okay, so now let me manipulate these numbers. So now for this one, I see 4 squared. I think 4 squared is 16, right? So I have, oh, this one is 4 times 16, which is the same as 16 minus 4. So that'll be 0. So that's just 6. Now, when I'm done, right, I have all the values, the function evaluated at each of these points, right? So the smallest is supposed to be my absolute minimum value, right? So from here, I can see that this is my smallest. So this is my absolute minimum value, right? And then the largest is 6. So that is my absolute maximum value. So to sum everything up, my absolute maximum value is 6, and it occurs at where? It occurs at 4, right? Because we evaluated a function at 4 to get this, right? And as I was saying, please be careful with what the question asks, right? It could ask you for the value or where it occurs at. Now, sometimes the absolute maximum or the minimum, the absolute minimum could occur at several points. So for example, you could have evaluated say f of 2 and get 6, and f of 4 also get 6, same 6, right? It doesn't matter, just that it occurs at 2 points, but then the absolute maximum is always a single value. Okay, now now we have the absolute maximum minimum. Okay, so this one too, it occurs at where? It occurs at 2, at s equal to 2. Let me add the s at s value equal to s equal to 2. Please, any questions on the closed interval method? And that's all. So in order to use a closed interval, the function has to be continuous and defined on the closed interval. Immediately you see those conditions are satisfied, just get the critical points, evaluate the function at the critical points, and then at the endpoints, the biggest value amongst those is your absolute maximum and value, and then the smallest among them is your absolute minimum value, and that's all. Please, any questions on this? Are you okay? Anybody needs time here? Okay, then that's the end of 4.1. Okay, so let's move on to 4.2. Now for 4.2, you're going to learn something we call the mean value theorem, right? Now for the mean value theorem, it goes as follows. To start a mean value theorem, you need to know something called the Rolle's theorem. Now for this one, all that you need to know is the conditions. If the conditions are satisfied, then something follows. So there'll be some conditions you have to check for a function. If those satisfy, then the final conclusion follows, right? So let's look at the Rolle's theorem. It says, let f be a function that satisfies the 3 hypotheses, right? The 3 hypotheses. So the first thing is the function is continuous on the closed interval. So if the function is continuous on the closed interval, 2, the function is differentiable on an open interval, a to b, right? Now, the third condition is the value of the function at a is equal to the value of the function at b. That means the value of the function at the endpoints are also the same. Now, if these 3 conditions hold, then the conclusion is there has to be a number, right? At least one. There could be more, but there has to be at least one. A number c, which has to not be at the endpoints, but in between the 2 endpoints, right? A and b. So there's a number c in between a and b such that the f prime of the c is equal to 0. The f prime of the c is equal to 0. Okay, so let's look at some graphs to see if this makes sense, if this adds up. So we look at some graphs, right? So let's look at these 4 graphs. Now for the first one, let's look at the conditions of the Rolle's theorem. Is the function continuous on a closed interval? Well, as you can see, the function is defined here, and there's a point right here for p. So the function is continuous, right? There's no break. So the function is continuous on a closed interval. Okay. Now the next thing is the function is different. Is the function differentiable? Well, if you remember what we learned in chapter 2, right? Differentiability means there are no sharp corners or kinks, there is no discontinuity, and there's no vertical tangent, right? Remember those three conditions for differentiability. Well, you look at the graph and you can see that there are no such rule violations, right? There's no sharp corner or kink, there's no discontinuity, there's no vertical tangent. So this one is differentiable, right, on the interval A to B. Okay, so the first two conditions are satisfied. Now the third one says the function value at the endpoints have to be the same. Well, if you read f of A is right here, right? And f of B is also right here. So f of A equal to f of B. So the third condition too is satisfied. Now what they're saying is if those conditions are satisfied, then there has to be at least one C in between A and B, such that the what f prime of the C equal to 0. Now, what does f prime of C equal to 0? What all that is saying is there is a C, a point in between A and B, said that the slope of the tangent line is 0. In other words, this one has a what? A horizontal tangent line. Well, as you can see, for this case, there are infinitely many points in between A and B where the slope of the tangent is 0. In fact, the slope of the tangent is 0 here, slope of the tangent is 0 here, slope of the tangent is 0, slope of tangent, slope of tangent, right? So for every point in between the A and B, this is satisfied, right? So this actually verifies the Rayleigh's theorem, right? The Rayleigh's theorem is illustrated here. Okay, now let's move on to the second graph. So for the second graph, let's run through the conditions, the hypothesis. First one is the function continuous on a closed interval. Yeah, this function is defined for A here, defined for B here, right? So the function is on a closed interval, right? It's continuous on a closed interval. The next thing is the function differentiable. Well, I don't see any sharp corners, or I don't see any like discontinuity, or I don't see any vertical tangents on the graph. So the function is differentiable on that interval. Now the final thing is if f of A equal to f of B, right? Well, when you read the values, you can clearly see that the f of A is equal to f of B. So yeah, so the third condition is also satisfied. Now, if the three conditions are satisfied, then what we are saying is there has to be a point C in that interval A to B such that what the slope of the tangent line is what? You have a horizontal tangent line, or the slope of the tangent line is 0. And for this one, when you track the slope of the tangent line along the curve, you see that C occurs here. At that point, the slope of the tangent line is 0. Right? So that's it. For this one, we had just one C, right? Just one C. But the rule is there has to be at least one C where this will occur. So this one too checks out. Fine. Now, when you look at the third one too, is the function continuous on a closed interval? Yeah, that's true. Is defined for these endpoints A and B, right? It's defined on a closed interval. And then the next thing is the function differentiable on that interval? Yeah, we don't see any sharp corners, we don't see any vertical tangents, and we don't see any discontinuity. So the function is differentiable. And then the final thing is f of A equal to f of B? Yeah, the f of A here equal to f of B, right? So the third condition is also satisfied. And then we are saying that there has to be at least one C. There could be more, but at least one C where the slope of the tangent line is 0. Okay, so when you track the tangent line, you see that this occurs here. This is one of the C's, and there's also another C. So here we get two C's where the slope of the tangent line is 0. Okay, now the last one. Now the function is continuous on the interval A to B, the closed interval A to B. The function is differentiable on the open interval A to B. And then the function at A and the function value at B are all the same. Okay, nice. All the conditions are satisfied. So that means by the Rayleigh's theorem, there has to be at least one C in between the A and B such that the f prime of the C is equal to 0. In other words, you have a horizontal tangent there, and this C occurs here. So all of these three graphs show you or illustrate the Rayleigh's theorem idea. Please, any questions here? Anybody needs time here? Okay. Now you see that for the ones that I showed you, the Rayleigh's theorem is plausible, right? It makes sense. It adds up. Now let's move on to the mean value theorem, which is the main heading. Now let's run through the rules for the mean value theorem. For this one too, it's similar to the Rayleigh's theorem, right? And in a sense, this one is more general than the Rayleigh's theorem. I'll show you what I mean by that very soon. So the mean value theorem just has two hypotheses, right? It says the function has to be continuous on a closed interval, and the function is differentiable on an open interval. Basically, the first two conditions of the Rayleigh's theorem. Now it misses the third. It just says omit the third condition. The third condition for the Rayleigh's theorem says the f of A and the f of B have to be equal. But this one says just omit that, right? So just take the first two. The function is continuous and the function is differentiable. If those two conditions hold, then the f prime of C equal to what? F of B minus f of A all over B minus A. Now, as I was saying, the Rayleigh's theorem is a special case of the mean value theorem. The mean value theorem becomes the Rayleigh's theorem when the f of B is equal to f of A. That was the last condition that we omitted. Because when f of B is equal to f of A, then this one is just going to be, the numerator here is going to be 0. Right? It will be 0. And then everything will reduce to f prime of C equal to 0. So that means this one is more general to learn than the Rayleigh's theorem. Okay. Now let's try and make sense of what is happening here. Right? Let me cancel this so that it doesn't create any confusion for. I'll just illustrating the mean value. Okay, and the Rayleigh's theorem comparison. Okay, so now let's try and make sense of this formula here, the conclusion here. Right. So what we are saying is if the function is continuous on closed interval HB and then differentiable on open interval HB, then there has to be a C in between such that the f prime of C equal to f of B minus f of A all over B minus A. Well, if you look at this formula that you see here, right, then we know that the f prime of C is just the slope of the tangent line in between the slope of the tangent line at C. Okay, now what about the f of B minus f of A all over B minus A? Well, this looks like a rise over run because is the y coordinate at B minus the y coordinate at A all over what? B minus A. So this represents the slope of the line passing through the point, the endpoints, passing through the endpoints. So basically what this is saying is whenever the conditions hold, then there has to be a point C in between the A and B such that the slope of the tangent line equals to the slope of the secant line passing through the endpoints A and B. Right. So that's all geometrically, that's what this means. Right. So I'll show you a graph which will make it add up a lot. So let's look at these two. So now looking at the mean value theorem, we say, okay, now is the function continuous? So let's consider figure 3, right? Is the function continuous on the closed interval? Well, the function is defined at A and B, right? At A, we have it here defined, and then at B, we have it here. So the function is in black, right? In black here. And then, okay, so if the function is continuous on that point, let's check the second condition. Is the function differentiable on the open interval? Well, the function is differentiable because I don't see any sharp corners or like a kink or anything. I don't see any discontinuity. I don't see any vertical tangent. So the function is differentiable. Okay, now, then the conclusion follows. It says there is a point C, at least one point, right? There could be more. At least one point C in between the A and B such that the slope of the tangent line will be equal to the slope of the secant line, which passes through the A and B. So looking at this point, right? Looking at the A and B, the slope of the secant line is like, you see the secant line in blue. This is the secant line. So look at the slope of this secant line. Well, if I track the slope of the tangent line, right, you see that when I get to this point C here, the tangent line slope is the same as the secant line slope. So this verifies the mean value theorem. Right. So that's one way of seeing this. Right. That's an example. Now let's look at the other way, the other example. So for fig 4, we have the C's being the C occurring at 2 points. Right. So there's like more than one. So let's consider the hypothesis. So the first condition is the function continuous. Well, the function is continuous in the closed interval A to B, right? The function is continuous. The function is the function differentiable? Well, we don't see any sharp corners. We don't see any vertical tangents. We don't see any discontinuity. So the function is what differentiable from A to B. Then the question is, let's consider the slope of the secant line. The slope of the secant line is in blue, right? The secant line passing through the endpoints. This is the blue, right? So you can see this line. Now, when you track the tangent slope, the tangent line, you see that at this point, the tangent line slope is equal to what? The blue line. And also at this point, also the tangent line slope is also equal to the slope of the blue line. So that's it. That's the Rayleigh's theorem. Sorry, the mean value theorem actually. Okay, please, any questions here? Okay. Now another connection with the Euler theorem is that I want you to see is what we are saying is if you use the mean value theorem idea on the Euler theorem, just consider just one of the graphs, say B. When you consider the secant line which passes through the endpoints, then the secant line here is always going to be flat. If the endpoints are the same values, then whenever you grab a line to join the 2 points, then to be flat, you see, so the slope of such a line will be 0. And then what is the f prime of C? It says that f prime of C is also equal to 0. So still the mean value theorem idea is a more general one because it still says the slope of the tangent line in between the points will also be equal to the slope of the secant line, right? Joining the endpoints. So if the slope of the endpoint, the secant line joining the endpoints is 0, it's horizontal, then we expect that the f prime of C, which is the slope of the tangent line in between the A and B, will also be 0. So which will be the Euler's theorem, right? So I'm just saying that the Euler's theorem is a special case of the mean value theorem. Okay. So now let's see how this works. So this is just talking about what I just said. Right? So secant line AB. There's a point where the tangent line is parallel to the secant line. So they have the same slope. So let's see how an example goes. These ones are usually very straightforward and simple, right? So no need to stress about mean value theorem questions. You just have to be careful that all the conditions are satisfied. If all of them are satisfied, then usually the question will ask you to find the C where it occurs at. So they are very, very straightforward, right? They are very straightforward. Okay, so now let's look at this question. So for this one, we are considering a polynomial s cubed minus x, and then the endpoints are a, 0, and b. So it's more like it's defined on this closed interval, so 0 to 2, something like this, right? So now let's see. I think the solution is on here, so I'll work on the whiteboard so that we can see how this works together. So this 4.2 mean value theorem. You're looking at example 3. Example 3. One slice. So let's see how typical questions appear. So the typical questions are like this, right? It's not as complicated. It's not that complicated. So you have f of x equal to s cubed minus x, and then it's defined on this point. So the question is, for this closed interval, is the function continuous, right? So check, is the function continuous? Yeah, the function is a polynomial. Polynomials are continuous everywhere, right? So f is continuous on the interval. So yeah, it's continuous. And then the next thing is the function is differentiable. Yeah, polynomials are smooth. They are smooth. So they are also differentiable everywhere. Right? So it's also differentiable. Now, if these two conditions hold, then what we are saying is the conclusion is that there has to be a C in between this 0 and 2, such that this is the conclusion, such that the f prime of C equal to what? The f of B minus f of A all over B minus A. The slope of the tangent line is equal to what? The slope of the secant line, joining the two endpoints. So to get the f prime of C, we first find f prime of x. So f prime of s will be equal to what? 3s squared minus 1. So if f prime of s is 3s squared minus 1, the f prime of C will be what? 3c squared minus 1. Please, I hope you follow. Any questions up to this point? Okay, so we have the f prime of C. We have the left-hand side of the equation, right? Now we are trying to solve the C. That's the goal of this question. We are trying to solve for the C, where it occurs at, where the point in between the A and B such that what the slope of the tangent line equal to the slope of the secant line. That's what we are trying to find. Okay, so we just set up this equation and solve. Okay, so I also need f of B minus f of A, right? So let me try and find the f of B. The f of B is the f of the upper endpoint, right? So let me look at f of 2. F of 2 just be 2 cubed minus 2. So that'll be 8 minus 2, which is 6. And then the f of A is f of 0, which is going to be 0 cubed minus 0. And that is just going to be 0. Okay, so I have the two endpoints, right? The value. So fixing everything together in this equation, I have f prime of C, which will be 3c squared minus 1, equal to f of B, 6 minus f of A, 0, all over B minus A. What is B? B is 2 minus A, which is 0. Right, so solving this, I have 3c squared minus 1 equal to 6 divided by 2 is 3. And then I have 3c squared equal to, and then 3 plus 1, that is 4. right? So divide both sides by 3. You have c squared equal to 4/3, right? So that means c equal to what? Plus or minus square root of 4/3, which will give you c equal to square root of 4/3 is 2 over square root of 3. So either square root of 2, no. So either 2 over square root of 3 or c equal to negative 2 over square root of 3. But please remember that the c has to be in between the 0 and 2, right? C has to be in between 0 and 2. That means that the negative 2/3 cannot be that c. This is not part of the solution. Right? Because not in the interval 0 to 2, right? It's negative. So you have to exclude this. Now, 2 over square root of 3 is obviously in between 0 and 2 because we are dividing 2 by a positive number. When you divide 2 by a positive number, which is greater than 1, it has to be less than 2. So it has to be less than 2 and also positive. So 2 over 3. But if you want to check, you can use your calculator. This is going to be in the interval 0 to 2. So that means that's our C. This is where the slope of the tangent line will be called what? The slope of the secant line joining the endpoints. So that's all. I need to move on to the next slide to make the conclusion. Or maybe I can just do it here. Let me just put a box around this. So there's the point. So at C, the slope of the tangent line will be called what? The slope of the secant line joining the points. Okay. Please, any questions here? Any part you don't understand? So that's the mean value theorem. The questions around these are usually quite straightforward. Okay. Anybody needs more time here? Okay. Then let me switch. So now let's just run through this is just going to talk about what I just said, right? So the function is continuous. It's a polynomial, so it's continuous and differentiable. So by the mean value theorem, it just found it used the formula, right? So, and then found this. It used it's the same formula, but you see for here, it used this one. There are 2 parts to this formula. The second one is just the first one simplified. When you multiply both sides by b minus a, you get this one. Right? So no harm done. You can still use this idea. I like using this idea because of the geometric interpretation, relating the slope of the tangent line to the slope of the secant line joining the 2 endpoints. So that's why I prefer this one. Yeah, but yeah, you can also use this, which is what the question used, right? So found this, found f of 2, evaluate everything. But then the c must lie in between 0 and 2. So we concluded that the c is what? Is 2 over square root of 3. And that's all. So this is just showing us a graph, like in an illustration. And so we have the function given in black, and we are defining it on a closed interval, right? So from 0 to 2. So the secant line joining the points is like so. Right? You see, it's like so. So what you're saying is there has to be a c, at least one c, in between a and b, said that what the slope of the tangent line will also be equal to the slope of this secant line. And you can see that this c occurs here. And that's the point you found, 2 over square root of 3. Please, any questions here? So the questions are quite straightforward. Now let's look at another application of this mean value theorem. When is it also useful? Is it always that the question is going to ask us to find a c if the hypotheses are satisfied? Well, there's another twist. So let's look at this. Suppose that f of 0 equal to -3 and f prime of x is less than or equal to 5 for all values of x. How large can f of 2 possibly be? Okay, so let's look in this question. I think the solution is on here. Yeah, the solution is on this. Yeah, so I'll do this on a whiteboard. Okay, so let me go to the whiteboard. So this is example 5. Okay, so we have f of 0 equal to -3. And we have f prime of x less than or equal to 5 for all x. The question is asking for how large can f of 2 possibly be? Now let's see how the mean value theorem can be applied in this question. So the mean value theorem, first and foremost, right? In order to even think about using it, you have to make sure the two hypotheses are satisfied. Okay, now I'm trying to find some information about f of 2. And then the question has also given me f of 0. So it's safe to think that if I'm going to apply the mean value theorem, I need some points A and B, right? So if I'm going to investigate the behavior at f of 2, then it's good that I try and consider. Okay, that's fine. Yeah, that's fine. Let me see the name. It's too small. Is it Nina? Yeah, Nick. Yeah, that's fine. Okay, so now, so what we are saying is, we have to consider, we have been given information about the function at 0, and we need information at f of 2, and we want to use the mean value theorem. So we have to consider a function which is defined in between 0 and 2, right? So consider a function defined in between 0 and 2. So the question is, if you consider such a function, given the conditions, does this function satisfy the conditions of the mean value theorem, the hypothesis of the mean value theorem? First thing, we are not given any information about whether the function is continuous, right? If we consider the function to be on this closed interval. But note one thing. We know that f prime of s is less than or equal to 5 for all values of s. That means that f prime of s, the value is known. We can obtain a value for all values of s, right? So what this means is the function is differentiable for every x. But the question is, if we know the function is differentiable, does it mean the function is continuous? And I throw that question to you. The fact that function is differentiable doesn't mean it's continuous. We learned this in 2.5 when we were at continuity, and I told you we use it at some point in chapter 4. So there's the point. If the function is differentiable, does it mean it's continuous? Anybody? Do you remember? Yes, thank you, Lena. It's true. If the function is differentiable, then it means it's continuous, but not vice versa. The fact that the function is continuous doesn't mean it's differentiable on that point, right? So in this case, because the function is differentiable for all x, we can say that, okay, we know that the function is also what? It's continuous, right? If it's differentiable on an interval, then it's continuous. Okay, so now that we know that the two conditions have been satisfied, that means we can safely use the conclusion of the mean value theorem, which says that the f prime of c, there has to be a c in between the such that what? The value at the endpoints, the slope of the secant line joining the endpoints will be equal to the slope of the tangent line. Okay, now, because we know that f prime of s is less than or equal to 5, that means that f prime of c will also be less than or equal to 5. Right? It's less than or equal to 5 for all x. F prime of s is less than or equal to 5 for all x. So f prime of c will also be less than or equal to 5. And then what is f of b, f of a? Because f prime of c is equal to f of b minus f of a, minus f of all over b minus a, we can also say that because this will be less than or equal to 5, this will also be less than or equal to 5. And then what is the f of b? Well, the f of b is f of 2. What is f of a? F of a is f of 0. What is b minus a? Is 2 minus 0, less than or equal to 5. But what is f of 2? That is what we are trying to find information on. What is f of 0? That is already given here. And then we divide it by 2, less than or equal to 5. So from here, you have f of 2 plus 3, less than or equal to, multiply both sides by 2, you get 10 on this side. You get f of 2 is less than or equal to 7. That means the largest possible value is what? Is 7. F of 2 has to be less than or equal to 7. Please, are you okay with this? Any issues with the calculation? Now, this is the last thing I'll do. I'll have to go to the PowerPoint and we'll go through the slides to see where we're at so that I'll record that. But this is the last thing. Please, any part you don't understand, is there any question, any issues, any concerns? Anybody needs time? Yeah, there'll be a solution on the PowerPoint anyways. So, okay, so then let me go to the PowerPoint, go through it and see where we're at. Right, so we are giving a differential, well, therefore continuous. It's basically doing what I just did. All right, so solve everything. So we get f of 2 equal to 7. And so we are here. This is the last. Oh, this also happens to be the last slide. Yeah, so we are here. We would look at this on Friday, right? So that'll be all. So thank you for your time. Please feel free to reach out if you don't understand anything. Don't wait till it piles up, right? I'm here to assist. So just send me an email or schedule an office hours time, right? If you need time and if you need me to explain or do more examples with you. If you also have issues with homework, you can also talk to me or any of your TAs. So that's all for today. Thank you for your time. All the best. You are welcome.